There are more stars in the observable universe than grains of sand on every beach, every desert floor, and every ocean bed on Earth combined. That comparison gets used so often, it has lost its impact. So instead of repeating it, consider what it actually implies. Each of those stars is a nuclear furnace, converting millions of tons of hydrogen into helium every second. Each of them sits alone in the dark, separated from its nearest neighbor by distances so vast that the fastest thing in physics needs years to cross them. And on average, each of them hosts at least one planet. That is not a poetic estimate. It is a statistical conclusion drawn from monitoring over 150,000 stars. Before we dive deeper, if this kind of content genuinely interests you, consider subscribing because what you're about to see only gets more surprising from here. And I post videos like this every single day. Now, let's continue. The number of worlds that must exist in the cosmos is no longer seriously in doubt. What remains genuinely difficult to grasp is the scale at which all of this is arranged. Not because the measurements are imprecise, but because the human brain was never built to process them. Every intuition you have about distance, about size, about what counts as far away, was forged over millions of years of evolution on the surface of a single small planet. The spatial reasoning you rely on every day is exquisitely calibrated for throwing distances and walking ranges. It has no natural capacity for the measurements we are about to move through. Every step in the journey from here to the edge of the observable universe will destroy the sense of scale you built at the previous step. This is not a rhetorical device. It is what the actual numbers do, reliably, every time. Start with yourself. You are roughly 1 8/10 meters tall. Your brain uses that height as its baseline measurement for every distance it has ever navigated. The hallway to the kitchen, the walk to a shop, the length of a city block. Your ancestors needed to judge the gap to a water source or the width of a river crossing. That is what the spatial reasoning machinery in your skull was optimized for. It was not optimized for what comes next. The tallest structure humans have ever constructed is the Burj Khalifa in Dubai, standing 828 meters above the ground. If you stood at its base and looked straight up, your sense of proportion would already begin to wobble. Stack 450 people, head to toe, and you approximate its height. By any standard your brain applies to daily experience, 828 meters is enormous. Mount Everest rises to 8,849 meters above sea level, more than 10 times the height of that building. Climbers who reach its summit describe looking down at clouds and sensing the faint curvature of the Earth along the horizon. The atmosphere thins to the point where survival without supplemental oxygen becomes a calculation measured in minutes. Hundreds of people have died attempting that summit. Thousands more have returned with permanent physiological damage. By every human standard, Everest represents the most extreme environment accessible on foot. And yet, Everest is essentially a surface blemish. If you shrank the Earth to the size of a billiard ball, that mountain would be invisible. The planet would actually be smoother than a standard billiard ball, which contains shallow dimples that, at planetary scale, would represent features taller than Himalayan peaks. Earth measures just under 12,756 kilometers in diameter. If you drove a car straight through the planet at highway speed without stopping, the journey would take roughly 5 days. The circumference at the equator stretches approximately 40,075 kilometers. A commercial airliner, cruising at nearly 900 kilometers per hour, would need a little over 45 hours of continuous flight to circle the globe once without landing. 2 days in an aircraft, and you have wrapped around an entire world. Your brain can almost accommodate that. Now leave the surface. The International Space Station orbits Earth at an altitude of approximately 400 kilometers, completing one full lap of the planet every 90 minutes. Astronauts aboard it are moving at roughly 28,000 kilometers per hour. From that altitude, Earth fills most of the view. Continents drift past beneath them. Storms spiral across blue oceans. The planet looks vast and alive. But the station is barely above the atmosphere. If Earth were a basketball, the station would orbit less than 6 millimeters above its surface. You would need a magnifying glass to see the gap. That is how close humanity's permanent presence in space is to the ground beneath it. The moon changes everything. It orbits at an average distance of 384,000 kilometers, roughly 30 Earth diameters placed side by side. When the Apollo astronauts traveled there, the journey took approximately 3 days. 3 days of coasting through absolute emptiness. Earth shrinking behind them. The gray cratered moon growing slowly in the forward window. Radio signals between mission control and the spacecraft experienced a delay of about 1.25 seconds in each direction. When you make a phone call across a city, you'd expect an essentially instant response. At the moon's distance, the speed of light already introduces a noticeable pause. 1.25 seconds for a question to arrive. 1.25 seconds for the reply to return. A nearly 3-second round-trip delay. And that is only the moon, the nearest object in the sky of any real significance. The sun sits approximately 150 million kilometers from Earth. Astronomers call this distance 1 astronomical unit, and it serves as the standard measurement for everything within our solar system. If you drove a car toward the sun at 100 kilometers per hour without stopping, the journey would take over 170 years. A commercial jet traveling at 900 kilometers per hour would need roughly 19 years of uninterrupted flight. Light, the fastest thing that exists, needs 8 minutes and 20 seconds to cover the distance. Every time you look at the sun, you see it as it appeared more than 8 minutes ago. If the sun vanished right now, you would not know for another 8 minutes. The gravitational signal traveling at the same speed would take the same amount of time, and during those 8 minutes, Earth would continue orbiting a point in space where nothing remained. The sun itself defies comfortable visualization. Its diameter spans 1,392,000 kilometers. You could line up 109 Earths across its face. Its volume could contain approximately 1,300,000 Earths. It accounts for nearly 99.9% of all the mass in the solar system. Jupiter, the largest planet, a gas giant so massive it could contain all the other planets combined, is still roughly 1,000 times less massive than the Sun. Earth orbits a furnace so dominant that everything else within its gravitational reach is a rounding error by comparison. Mars orbits at an average distance of 228 million kilometers, approximately 1.5 astronomical units. At its closest approach to Earth, the gap narrows to about 54 million kilometers. Even at that minimum distance, a radio signal traveling at the speed of light takes roughly 3 minutes to cross the void. Mission controllers sending commands to a rover on Mars must wait between 6 and 44 minutes for a round-trip signal, depending on where the two planets sit in their respective orbits. The rover cannot be driven in real time from Earth. It operates autonomously, making its own decisions in the moment, because real-time guidance across that distance is physically impossible. Jupiter orbits at 5.2 astronomical units, approximately 779 million kilometers from the Sun. Saturn orbits at 9.5 astronomical units. At Saturn's distance, sunlight is roughly 100 times dimmer than it appears from Earth. A person standing on one of Saturn's moons would see the Sun as an extraordinarily bright star rather than the blazing disk we know. Radio signals from the Cassini spacecraft orbiting Saturn took between 67 and 85 minutes to reach Earth. Data from those distant observations arrived on scientists' screens more than an hour after the spacecraft recorded it. Neptune sits at approximately 30 astronomical units, 4.5 billion kilometers from the Sun. At that distance, sunlight takes over 4 hours to arrive. A spacecraft traveling from Earth to Neptune, as Voyager 2 did, required 12 years to make the journey. 12 years of flight through mostly empty space, past gas giants and their moons, through radiation belts, deeper and deeper into a solar system that kept revealing how much farther it extended than anyone intuitively expected. Voyager 1 launched in September of 1977. As of early 2026, it has been traveling for over 48 years and has reached a distance of approximately 165 astronomical units from the Sun. That translates to more than 24 billion kilometers. Voyager 1 crossed the boundary of the heliosphere, the bubble of charged particles the Sun pushes outward into surrounding space, in August of 2012, becoming the first human-made object to enter true interstellar space. 24 billion kilometers sounds like the edge of everything. It is not even close to the edge of anything. The Oort cloud marks the true outer boundary of the Sun's gravitational reach. This theoretical shell of icy bodies surrounds the solar system in a roughly spherical halo extending from about 2,000 astronomical units to as far as 100,000 astronomical units. Objects within the Oort cloud take millions of years to complete a single orbit around the Sun. Comets that fall inward from this remote reservoir and streak past Earth on long elliptical paths may not return for tens of thousands or even millions of years. At Voyager 1's current speed of roughly 61,000 kilometers per hour, the spacecraft would need approximately 300 years to reach the inner edge of the Oort cloud. It would require roughly 30,000 years to pass through the cloud entirely and emerge on the other side. 30,000 years. The entirety of recorded human civilization spans roughly 10,000 years. Voyager would need to fly for 3 times the entire span of human history just to cross one structure within our own solar system. And even after emerging from the other side, it would still not have reached the nearest star. The closest stellar neighbor to our Sun is Proxima Centauri, a dim red dwarf sitting 4.24 light-years away. Light itself, traveling at nearly 1 billion kilometers per hour, needs over 4 years to travel from here to there. Voyager 1, our fastest human-made emissary, would need roughly 73,000 years to reach Proxima Centauri if it were heading in that direction. 73,000 years. The last ice age ended about 11,700 years ago. Voyager would need to fly for more than 6 ice ages, laid end to end, before it reached the nearest star. To feel what that distance means at a human scale, consider a scale model. If you shrank the Sun down to the size of a golf ball and placed it on a table, Earth would be a grain of fine sand orbiting about 4.5 meters away. Jupiter would be a small pea circling at roughly 23 meters. Neptune would orbit at about 137 meters. The Oort cloud would extend outward for roughly 90 kilometers in every direction. A gravitational territory the size of a metropolitan region surrounding one golf ball, and Proxima Centauri, the nearest neighboring golf ball, would sit approximately 1,200 kilometers away. 1,200 kilometers of absolute emptiness between 2 tiny spheres. That is the interstellar neighborhood. That is how far apart stars actually are. This emptiness defines the solar system's true character. The planets feel like a crowded family when you see them illustrated in textbook diagrams, neatly spaced along colorful orbital lines. Those diagrams compress distances by factors of thousands to fit on a page. In reality, the solar system is almost entirely vacuum. If you threw a dart randomly into the volume of space enclosed by Neptune's orbit, the odds of hitting anything, any planet, any moon, any asteroid, are so microscopically small they are effectively zero. Space is not simply large. It is profoundly, relentlessly, overwhelmingly empty. Between stars, the interstellar medium contains roughly 1 atom per cubic centimeter. The air you're breathing right now holds approximately 25 quintillion molecules per cubic centimeter. The difference between those two numbers is so extreme that interstellar space qualifies as a better vacuum than anything ever produced in a laboratory on Earth. Yet this emptiness is not featureless. Vast clouds of molecular hydrogen drift between stars, some stretching dozens of light years across. These molecular clouds are stellar nurseries, regions where gas slowly accumulates under its own gravity until pockets of it collapse, heat up, and ignite nuclear fusion. Every star you have ever seen was born inside one of these clouds. The Sun itself formed roughly 4.6 billion years ago from a collapsing region within such a cloud that no longer exists. The material that became Earth and eventually became you was once scattered through interstellar space as atoms of hydrogen, helium, carbon, oxygen, and iron drifting in the void between stars that had already lived and died. The iron in your blood was forged in the core of a massive star that exploded as a supernova billions of years before the solar system formed. The calcium in your bones was produced by a different type of stellar explosion. The oxygen you breathe was fused in the furnace of yet another star. You are not metaphorically constructed from stellar material. You are materially, chemically, atomically built from elements manufactured inside stars and ejected into interstellar space through violent deaths. Stars themselves are enormously diverse. The Sun is a yellow dwarf, a middle-aged, medium-temperature star that will burn steadily for roughly 10 billion years before swelling into a red giant and eventually collapsing into a white dwarf, roughly the size of Earth. It represents the most ordinary category of star imaginable. Red dwarfs are the most common stars in the Milky Way, accounting for roughly 70 to 75% of the entire stellar population. They're small, dim, and cool, with surface temperatures ranging from roughly 3,000 to 4,000 degrees Kelvin. The smallest red dwarfs contain only 8% of the Sun's mass, barely enough to sustain hydrogen fusion in their cores. What they lack in brightness, they compensate for in longevity. A red dwarf burns its fuel so slowly that it can shine for trillions of years, far longer than the current age of the universe. Every red dwarf that has ever ignited is still burning today. Not one has had enough time to die. At the opposite extreme sit the blue supergiants, stars so massive and so hot that they burn through their nuclear fuel in just a few million years. A blue supergiant can contain 50 or even 100 times the mass of the Sun, with surface temperatures exceeding 30,000 degrees Kelvin. Their luminosity outshines the Sun by factors of hundreds of thousands. A single blue supergiant can produce more energy per second than an entire cluster of red dwarfs generates in a year. But their ferocity is their undoing. These stars fuse progressively heavier elements in their cores until they reach iron, at which point nuclear fusion can no longer sustain them against gravitational collapse. The core implodes in a fraction of a second. The outer layers are blasted outward in a supernova explosion that can briefly outshine the entire galaxy containing it. What remains depends on the original mass. Some supernovas leave behind neutron stars, objects so dense that a single teaspoon of their material would weigh roughly 6 billion tons at Earth's surface. The most massive leave behind black holes, regions of space-time where gravity has become so intense that nothing, not even light, can escape. Neutron stars pack roughly 1.5 times the mass of the Sun into a sphere only 12 kilometers across. Their density exceeds 100 trillion times the density of water. Some neutron stars spin hundreds of times per second, emitting beams of radiation that sweep across space like cosmic lighthouses. These are pulsars, and their timing signals are so precise they rival atomic clocks in accuracy. Others possess magnetic fields 1 trillion times stronger than Earth's, powerful enough to disrupt electronics from enormous distances. These objects, called magnetars, occasionally release bursts of energy so intense that a single flare can compress Earth's magnetosphere even from tens of thousands of light years away. The Milky Way contains an estimated 100 million to 1 billion neutron stars, and perhaps 100 million stellar mass black holes, all remnants of massive stars that lived and died over the galaxy's 13 billion year history. These objects drift through the galactic disk and halo, invisible unless they interact with nearby matter. You could pass within a few light years of a black hole and never know it was there. The galaxy is a recycling engine. Stars form from gas, burn for millions or billions of years, eject enriched material back into space when they die, and that material is gathered up again by gravity into the next generation. Each successive generation of stars contains a slightly higher proportion of heavy elements than the last. This is why planets like Earth can exist. The first generation of stars formed from the nearly pure hydrogen and helium left over from the Big Bang could not have hosted rocky worlds, because the heavy elements needed to build rock and water did not yet exist in significant quantities. It took billions of years of stellar nucleosynthesis, billions of years of supernovas and stellar winds scattering material into space, before the galaxy's chemical inventory was rich enough to produce a planet capable of supporting complex chemistry and eventually life. Earth is a late-generation product. It exists because generations of stars lived and died before the Sun was born. This brings us to one of the most consequential discoveries in recent astronomy. Planets are not rare curiosities. They are everywhere. The Kepler Space Telescope, which operated from 2009 to 2018, detected over 2,700 confirmed exoplanets by monitoring the brightness of more than 150,000 stars and watching for the tiny dips in light caused by planets crossing in front of their host stars. Statistical analysis of Kepler's results led to a remarkable conclusion. On average, every star in the Milky Way hosts at least one planet. Many host several. Rocky worlds in the habitable zone, the orbital region where liquid water could persist on a planetary surface, may number in the tens of billions within our galaxy alone. 400 billion stars, tens of billions of potentially habitable rocky worlds, all spread across a structure 100,000 to 200,000 light years in diameter. That diameter represents the visible disk of the Milky Way, though the galaxy does not end where the bright stars thin out. The disk of stars is remarkably flat compared to its width. At the Sun's position, the stellar disk measures roughly 2,000 light years in thickness. The ratio of diameter to thickness makes the Milky Way proportionally flatter than a compact disk. If you scale the galaxy down to the diameter of a dinner plate, the disk would be thinner than a sheet of paper. This extreme flatness results from the galaxy's rotation. The rotating mass of stars and gas settled over billions of years into a thin plane where matter concentrates most densely. The Sun orbits the galactic center at a distance of roughly 26,000 light-years, placing us approximately halfway between the core and the outer edge of the visible disk. We occupy one of the galaxy's spiral arms, specifically a structure called the Orion Arm or local spur, which branches between the larger Perseus Arm and the Sagittarius Arm. Our position is not special. It is suburban. We live in a galactic neighborhood, neither densely packed near the core nor sparsely populated in the outer reaches, but somewhere in between, where stars are spaced a few light years apart and the night sky contains enough visible stars to inspire wonder. The galactic center, by contrast, is a place of extraordinary density and radiation. Stars near the core are packed thousands of times more tightly than in our neighborhood. If Earth orbited a star near the galactic center, the night sky would blaze so brightly with nearby suns that true darkness would never fall. You could read a book by starlight alone, but that brilliance would come with danger. Stellar encounters would be more frequent. Gravitational perturbations could destabilize planetary orbits. Radiation from nearby supernovas and from the central black hole would bathe everything in lethal energy. At the very center of the Milky Way sits Sagittarius A star, a supermassive black hole with a mass of roughly 4 million times that of our Sun. This object was confirmed through decades of careful observation. Astronomers tracked individual stars orbiting the galactic center and measured their trajectories with extraordinary precision. One star, designated S2, completes an orbit around Sagittarius A star every 16 years, reaching speeds of roughly 2% of the speed of light at its closest approach. The only object massive enough and compact enough to produce those orbital velocities without being visible is a black hole. In 2022, the Event Horizon Telescope collaboration released the first direct image of Sagittarius A star, showing the glowing ring of superheated gas swirling around the black hole's shadow. The image confirmed what decades of indirect evidence had established. Despite its enormous mass, Sagittarius A star is surprisingly quiet compared to supermassive black holes in other galaxies. Some galactic centers are active, blasting jets of material thousands of light years into space and outshining all the stars in their host galaxy combined. Sagittarius A star is dormant, consuming very little material at present. But observations of structures called Fermi bubbles, enormous lobes of high-energy gas extending above and below the galactic plane, suggest that the central black hole experienced a period of intense activity several million years ago, producing outbursts that sculpted the gas distribution across tens of thousands of light years. The monster is sleeping. It has not always slept. The galaxy rotates, but not like a solid wheel. Stars at different distances from the center orbit at different speeds in a pattern called differential rotation. The Sun travels around the galactic center at roughly 828,000 kilometers per hour. Even at that extraordinary velocity, one complete orbit takes approximately 230 million years. Astronomers call this period a galactic year. The last time the Sun was at its current position in its orbit, dinosaurs had not yet appeared on Earth. In the entire 4.6 billion year history of the solar system, the Sun has completed only about 20 galactic orbits. The galaxy operates on timescales that make geological ages feel brief. Differential rotation creates the spiral arms. These arms are not permanent structures made of the same stars. They are density waves, regions where stars and gas temporarily bunch together before moving on, similar to how cars slow and cluster in a traffic jam even though individual vehicles pass through. New stars form preferentially inside the arms because the higher gas density triggers gravitational collapse. This is why spiral arms glow brighter than the spaces between them. Beyond the bright disk, the galaxy possesses a vast spherical halo populated by ancient stars, globular clusters, and enormous quantities of dark matter. Globular clusters are dense spherical collections of hundreds of thousands to millions of stars bound together by mutual gravity. The Milky Way hosts roughly 150 known globular clusters, many of which orbit far above and below the galactic plane. These clusters are among the oldest objects in the galaxy, with ages reaching 12 to 13 billion years. They formed when the universe itself was young, before the Milky Way had fully assembled into its current structure. Stellar streams thread through the halo as well. These ghostly rivers of stars form when the Milky Way's gravity captures and tears apart smaller galaxies or globular clusters that wander too close. The captured stars stretch into long, thin trails that orbit through the halo for billions of years before fully dispersing. Mapping these streams reveals the gravitational field they move through, and that field extends far beyond the visible disk. Stars in the most distant known streams orbit at distances exceeding 200,000 light-years from the galactic center. Dark matter makes this possible. Roughly 85% of the Milky Way's total mass consists of dark matter, a substance that does not emit, absorb, or interact with light in any detectable way. Its presence is inferred entirely through gravitational effects. Stars in the outer galaxy orbit faster than they should, based on the visible mass alone. Without the additional gravitational pull from an enormous invisible halo, those outer stars would escape into intergalactic space. Dark matter provides the missing gravity, forming a spherical halo that encompasses the entire galaxy in an invisible gravitational structure. Estimates place the total mass of the Milky Way at roughly 500 billion solar masses, with the vast majority of that mass residing in the dark matter halo rather than in stars or gas. The bright, beautiful galaxy you see in photographs is the visible component of a structure that outweighs it by a factor of roughly 10. The Gaia Space Observatory, launched by the European Space Agency in 2013, has measured the precise positions and motions of nearly 2 billion stars in the Milky Way. This dataset revealed previously unknown stellar streams, mapped the three-dimensional structure of the spiral arms with new clarity, and confirmed that the galaxy's disk is warped, bending upward on one side and downward on the other. The warp likely results from gravitational interactions with the Large Magellanic Cloud, a satellite galaxy that orbits the Milky Way at a distance of approximately 160,000 light-years. Even at that distance, its gravitational tug is strong enough to distort the shape of the entire galactic disk. The Milky Way possesses at least 60 known satellite galaxies, with new, faint ones still being discovered. Most satellites are tiny dwarf galaxies containing only a few million stars, but their orbits reveal the total gravitational mass they are responding to. Every new satellite discovered pushes the known boundary of the galaxy's gravitational reach a little farther outward. The Milky Way is also a cannibal. It grows by consuming smaller galaxies that wander too close. The Sagittarius dwarf elliptical galaxy is currently being devoured, already stretched into a long stream of stars wrapping around the galactic halo. Within a few 100 million years, it will lose its identity entirely, its stars absorbed into the Milky Way's population. Forensic analysis of the Milky Way's stellar populations using chemical signatures and orbital data has revealed evidence of multiple past mergers. The most significant known event is the Gaia-Enceladus merger, which occurred roughly 10 billion years ago when a galaxy approximately 1/4 the Milky Way's mass collided and merged with ours. The remnants of that ancient galaxy are detectable today as a distinct population of stars with different chemical compositions and orbital characteristics than stars born natively in the Milky Way. All of this, the 400 billion stars, the spiral arms, the central black hole, the stellar streams, the dark matter halo, the satellite galaxies being digested, constitutes a single galaxy. One structure among an estimated 2 trillion in the observable universe. The nearest major galaxy, comparable in size to the Milky Way, is Andromeda, sitting approximately 2.5 million light-years away. Light leaving Andromeda tonight began its journey 2.5 million years ago, when the ancestors of modern humans were just beginning to use stone tools on the plains of Africa. Every photon from Andromeda that enters your eye carries information that old. You are not seeing Andromeda as it exists now. You are seeing it as it appeared before our species existed. 2.5 million light-years is the distance to our nearest large neighbor. That gap is roughly 10 times the diameter of the Milky Way itself. The entire Milky Way, with all 400 billion of its stars, could be placed in that gap approximately 12 times over with room to spare. Andromeda is falling toward us. The Milky Way and Andromeda are locked in a mutual gravitational embrace that has been pulling them together for billions of years. Andromeda approaches at roughly 400,000 kilometers per hour, closing the 2.5 million light-year gap with the patience of cosmic time. In approximately 4 to 5 billion years, the two galaxies will collide. Their spiral arms will distort. Their halos of dark matter will interpenetrate. Hundreds of billions of stars will rearrange themselves over the course of 1 billion years into a single, massive, elliptical galaxy that astronomers have preemptively named Milkomeda. Individual stellar impacts will be extraordinarily rare because stars are so widely separated. The Sun, if it still exists at that point, will likely survive the merger with its planets intact, flung into a new orbit around the combined galactic center. The violence of a galaxy collision is gravitational, not physical. It reshapes structure without smashing the components. The Milky Way and Andromeda are the two dominant members of a gravitational family called the Local Group. This collection includes more than 80 known galaxies, spread across a volume roughly 10 million light-years in diameter. Most members are dwarf galaxies containing only a few billion or even a few million stars each, approximately 54 million light-years from the Local Group. It contains over 1,300 known galaxies, packed into a volume roughly 15 million light-years across. At its heart sits Messier 87, a giant elliptical galaxy harboring a supermassive black hole with a mass of 6.5 billion solar masses, more than 1,000 times the mass of the black hole at the Milky Way's center. In 2019, the Event Horizon Telescope produced the first direct image of a black hole, using Messier 87's central object as its target, capturing the glowing ring of superheated plasma swirling around its shadow. That image had traveled 54 million light-years to reach us, meaning the light was emitted when the earliest ancestors of modern horses were first appearing on Earth. The Virgo cluster is not just larger than the Local Group. It represents a fundamentally different category of structure. Galaxy clusters are the most massive, gravitationally bound objects in the universe. They contain not only hundreds or thousands of individual galaxies, but also vast quantities of superheated gas called the intracluster medium. This gas, heated to tens of millions of degrees Kelvin by the gravitational energy of cluster formation, glows in X-ray wavelengths and actually contains more mass than all the stars in all the cluster's galaxies combined. The visible galaxies are islands floating in an ocean of invisible hot plasma, and surrounding everything, outweighing it by a factor of roughly 5, sits the cluster's dark matter halo. The total mass of the Virgo cluster, including galaxies, hot gas, and dark matter, reaches approximately 1.2 quadrillion solar masses. The local group itself is falling toward the Virgo cluster. Our entire galactic neighborhood, all 80-plus galaxies, is being pulled in its direction at roughly 400 kilometers per second. We will never reach it. The expansion of the universe is carrying the Virgo cluster away from us slightly faster than we are falling toward it. But the gravitational influence of the Virgo cluster is real and measurable. It distorts the motions of every galaxy in our region of space. At the centers of the largest galaxy, clusters sit the most massive galaxies in the universe. These brightest cluster galaxies contain up to several trillion stars and harbor supermassive black holes with masses reaching tens of billions of solar masses. The jets from these black holes can extend hundreds of thousands of light years into the surrounding medium, pumping enormous quantities of energy into the intracluster gas and preventing it from cooling and collapsing to form new stars. This feedback loop between black hole activity and cluster gas dynamics is one of the most active areas of current research in astrophysics. Zoom out further, and the Milky Way, the Andromeda Galaxy, the entire Virgo cluster, all of it dissolves into a single detail within a vastly larger structure called the Laniakea supercluster. Laniakea was identified and named in 2014 by a team led by astronomer Brent Tully. Laniakea spans roughly 500 million light-years and contains the equivalent mass of approximately 100 million billion suns distributed across an estimated 100,000 galaxies. The name comes from Hawaiian and translates roughly as immeasurable heaven, which turns out to be only a slight understatement. Laniakea was mapped not by counting galaxies, but by tracking their motions. Every galaxy in the universe has a peculiar velocity, a motion through space driven by the gravitational pull of nearby mass concentrations. By measuring the peculiar velocities of thousands of galaxies, Tully's team identified coherent flow patterns where galaxies across enormous volumes of space are all streaming in the same general direction. Laniakea is defined as the volume of space within which all galaxy motions converge toward a single gravitational focal point called the Great Attractor. This massive concentration of matter, partially hidden behind the dense dust of the Milky Way's plane, pulls everything within Laniakea toward it with a gravitational force that influences galaxy motions across hundreds of millions of light-years. To feel what 500 million light-years means, consider that light traveling from one edge of Laniakea to the other would need 500 million years to make the journey. When that light departed, the most complex life on Earth consisted of simple marine organisms. Fish had not yet evolved. The entire Cambrian explosion, the rise of vertebrates, the age of dinosaurs, the evolution of mammals, and the emergence of human civilization would all occur during that single beam of light's transit across one supercluster. Laniakea borders other superclusters. The Perseus-Pisces supercluster lies adjacent to it. The Shapley supercluster, one of the most massive concentrations of galaxies in the nearby universe, sits roughly 650 million light-years away and exerts its own enormous gravitational pull. Laniakea itself may be falling toward the Shapley supercluster as part of an even larger flow pattern that astronomers are still working to map. The hierarchy of gravitational structures does not stop at superclusters. It continues upward into the largest patterns of matter distribution the universe contains. If you could somehow step outside the universe and look at the distribution of all matter across billions of light years, you would not see galaxies scattered randomly through space. You would see a vast, interconnected network of filaments, walls, and nodes resembling the structure of a sponge, or the neural connections in a brain, or the pattern of soap bubbles in foam. This network is called the cosmic web, and it represents the largest scale organization of matter in existence. The cosmic web consists of 4 types of structures. Nodes are the densest regions, the intersections where multiple filaments converge, and galaxy clusters form at these nodes anchored by enormous concentrations of dark matter. Filaments are long thread-like bridges of dark matter and gas stretching between nodes, often spanning hundreds of millions of light years in length while maintaining widths of only 10 to 20 million light years. Walls are vast sheet-like surfaces where filaments meet to form broad planar structures containing thousands of galaxies arranged in thin layers. And between all of these structures lie the cosmic voids, enormous underdense regions where almost nothing exists. The filaments are the highways of the cosmos. Gas flows along them, funneled by dark matter's gravity toward the nodes where galaxy clusters grow. Galaxies form preferentially along filaments, strung out like beads on a string. In early 2025, an international research team, using an instrument called MUSE on the European Southern Observatory's Very Large Telescope, published an unprecedented high-definition image of a cosmic web filament connecting 2 galaxies at a distance, corresponding to when the universe was roughly 2 billion years old. The filament stretched approximately 3 million light years. For the first time, researchers could directly trace the boundary between gas inside galaxies and gas contained within the cosmic web itself. When compared to supercomputer simulations of cosmic structure, the observed filament matched theoretical predictions with remarkable precision. Also, in late 2025, a team led by researchers at the University of Oxford identified one of the largest rotating structures ever observed. A thin chain of 14 hydrogen-rich galaxies embedded within a much larger cosmic filament, roughly 50 million light-years long, and located about 140 million light-years from Earth. The galaxies within this thin strand were found to be spinning in the same direction as the filament itself, far more frequently than random chance would predict. This discovery challenged existing models of how galaxies acquire their rotational motion and suggested that the cosmic web may influence galaxy spin more strongly and over larger scales than previously believed. The European Space Agency's Euclid Space Telescope, launched in July 2023, released its first batch of survey data in March 2025, covering an initial deep field and revealing 26 million galaxies. Within these fields, the large-scale organization of galaxies along the cosmic web was already visible, with clusters connected by filamentary strands of galaxies stretching across billions of light-years of cosmic history. Euclid's mission will ultimately survey a third of the entire sky, measuring the shapes of billions of galaxies over 10 billion years of cosmic time, and constructing a 3-dimensional map of dark matter distribution on scales never before achieved. The structures revealed by these surveys are staggering. The Sloan Great Wall stretches approximately 1.4 billion light-years across, consisting of thousands of galaxies arranged in a wall-like formation. Even larger is the Hercules Corona Borealis Great Wall, detected through the clustering of gamma-ray bursts and estimated to span roughly 10 billion light-years. If confirmed at that scale, it represents a structure so immense that light would need more than 1/10 of the current age of the universe to travel from one end to the other. But the structures are only half the picture. The other half is emptiness. cosmic voids occupy roughly 80% of the universe's volume. These immense underdense regions, typically spanning 100 to 500 million light-years across, contain almost no galaxies. They are the hollow spaces between the filaments and walls, where matter has drained away under gravity's patient influence over billions of years. The Bode's void, discovered in 1981, stretches approximately 330 million light-years in diameter and contains fewer than 60 known galaxies. If the Milky Way sat at the center of the Bode's void, the nearest large galaxy would be so distant it would appear as a faint smudge detectable only through powerful telescopes. The night sky would be vastly emptier than what we see from our current position in the cosmic web. Dark energy, which appears to maintain constant density regardless of how much space expands, dominates voids completely. With so little matter to resist expansion, voids grow faster than the cosmic average, inflating and pushing their boundaries outward into the surrounding filaments. The cosmic web is slowly dissolving, its delicate structure being stretched apart by the relentless pressure of dark energy. Voids are getting larger. Filaments are getting thinner. The origin of all this structure traces back to the first moments after the Big Bang. During the epoch of cosmic inflation, in the initial fraction of a second, quantum fluctuations in the density of the primordial plasma were stretched to macroscopic scales. These fluctuations were extraordinarily tiny, variations of roughly 1 part in 100,000. But they were enough. Regions with slightly higher density attracted slightly more matter through gravity. Regions with slightly lower density lost matter to their denser neighbors. Over hundreds of millions of years, this process amplified. Dense regions collapsed into the first stars, which gathered into galaxies, which clustered into groups, which aligned along filaments. Underdense regions emptied further, expanding into voids. The cosmic web is the final product of gravitational amplification acting on quantum noise for 13.8 billion years. The largest structures in the visible universe grew from the smallest fluctuations physics allows. The cosmic microwave background radiation provides a snapshot of those fluctuations when the universe was just 380,000 years old. Satellites including COBE, WMAP, and Planck mapped tiny temperature variations across the entire sky, revealing the seeds of all future structure. Scientists feed these measured patterns into supercomputer simulations that model how gravity, dark matter, dark energy, and ordinary matter interact over billions of years. The resulting simulated universes produce cosmic webs that match the observed one with impressive fidelity. Filaments form in the simulations at the same scales and densities as real ones. Voids open up with the same sizes and emptiness. Galaxy clusters emerge at the nodes with comparable masses and temperatures. This agreement between theory and observation is one of the great triumphs of modern cosmology. But the agreement is not perfect. Some observed structures appear larger or more extreme than simulations comfortably produce. Supervoids estimated at nearly 2 billion light-years in diameter and showing significant density deficits are rare enough in simulations that their existence raises questions about whether our models fully capture the range of cosmic structure. These tensions are not crises. They are frontiers, places where observation pushes theory to evolve and improve. The Dark Energy Spectroscopic Instrument is currently conducting the most ambitious three-dimensional map of the cosmic web ever attempted, measuring precise distances to tens of millions of galaxies and quasars. Its early results, released in stages beginning in 2024, have already produced the most detailed picture yet of how cosmic expansion has evolved over the past 11 billion years. Combined with Euclid's wide field imaging and the James Webb Space Telescope's deep spectroscopy, these surveys are converging on a comprehensive understanding of how the cosmic web grew from primordial seas into the vast structure we observe today. All of this, the solar system, the galaxy, the local group, the Virgo cluster, the Laniakea supercluster, the cosmic web itself spanning billions of light years, exists inside a finite volume of space defined by how far light has traveled since the universe began. Beyond that boundary lies more universe, potentially infinitely more, that we have never seen and may never see. The observable universe has a diameter of approximately 93 billion light-years. That number requires careful unpacking because it contains one of the most commonly misunderstood aspects of modern cosmology. The universe is 13.8 billion years old. You might reasonably expect that the farthest thing we could possibly see is 13.8 billion light-years away. But the universe has been expanding throughout that entire time. Objects that emitted light 13.8 billion years ago were much closer to us when that light began its journey. During the billions of years that light has been traveling toward Earth, the expansion of space has been carrying those objects farther and farther away. By the time their ancient photons finally reach our telescopes, the objects themselves have been swept outward to a current distance of approximately 46.5 billion light-years. Double that to account for the opposite direction, and you get the full diameter of 93 billion light-years. The observable universe is vastly larger than the age of the universe naively implies, because space itself has been stretching while the light was in transit. This observable sphere is centered on Earth, not because Earth is special, but because the observable universe is defined by the observer's location. Every point in the cosmos has its own observable sphere centered on itself. An astronomer on a planet in the Andromeda galaxy would have a slightly different observable volume, overlapping with ours in most directions, but extending 2.5 million light-years farther in one direction and falling the same amount short in the other. Every observer sits at the center of their own visible cosmos. This is not a privilege. It is a geometric inevitability of finite light speed in an expanding universe. Within this sphere, current estimates place the total number of galaxies at roughly 2 trillion. Each of those 2 trillion galaxies contains anywhere from a few million to several trillion stars. Summing across the entire observable volume produces a total stellar population on the order of 10 to the 24th power. That is 1 septillion stars, written as a 1 followed by 24 zeros. In January 2026, astronomers confirmed that a galaxy designated MOMZ-14, discovered using the James Webb Space Telescope, is the most distant galaxy ever spectroscopically verified. Its light reveals the universe as it appeared just 280 million years after the Big Bang, corresponding to a redshift of 14.44. The galaxy is currently located approximately 33.8 billion light-years from Earth due to cosmic expansion during the intervening eons. It is brighter, more compact, and more chemically enriched than theoretical models predicted for galaxies forming so soon after the origin of the universe. Its existence, along with roughly 100 times more luminous early galaxies than standard cosmology anticipated, suggests that star formation in the infant universe was far more vigorous and efficient than scientists expected. The James Webb Space Telescope has not just pushed back our observational frontier. It has revealed that the early universe was assembling complex structures with a speed that challenges the models we built to explain it. The farthest boundary of our observable volume is not marked by distant galaxies. It is marked by a wall of light. The cosmic microwave background radiation is the oldest electromagnetic signal in existence. Released when the universe was approximately 380,000 years old and had cooled enough for the first stable atoms to form, this primordial light now arrives at Earth from every direction, stretched by 13.8 billion years of cosmic expansion into microwave wavelengths, with a temperature of approximately 2.725 degrees above absolute zero. It is extraordinarily uniform in every direction astronomers look. The temperature is the same to within a few hundred thousandths of a degree. This uniformity tells us that the early universe was almost perfectly smooth, with only the faintest ripples of density variation seeded by quantum fluctuations during inflation. Those ripples, mapped in exquisite detail by the Planck satellite, encode the initial conditions from which all cosmic structure eventually grew. Every galaxy, every cluster, every filament of the cosmic web traces its ancestry to the pattern of infinitesimal temperature variations in this ancient radiation. No electromagnetic telescope can see beyond it. Before the universe became transparent, no light was free to travel, so no images of earlier epochs can ever be captured using photons. The first 380,000 years of cosmic history are permanently hidden behind this wall of ancient radiation. Other observational windows may eventually pierce this barrier. Gravitational waves generated during inflation could carry information from even earlier moments. Neutrinos decoupled from matter about 1 second after the Big Bang, far earlier than photons, and a cosmic neutrino background should exist, though detecting it remains far beyond current technological capability. Beyond the observable universe lies more universe. How much more is a question that current physics can constrain, but cannot definitively answer. The most rigorous approach uses measurements of the spatial curvature of the cosmos. Measurements from the Planck satellite show that space is flat to within the precision of our instruments. This flatness implies that the universe is either infinite or vastly larger than the observable portion. Statistical analyses based on Planck data suggest that the total universe is at least 250 times larger in radius than the observable volume, corresponding to a minimum diameter of roughly 23 trillion light-years. If that lower bound is correct, the observable universe occupies less than 1 part in 15 million of the total cosmic volume. For every galaxy we can see, at least 15 million more exist beyond our horizon, and that is the conservative estimate. The true universe could be substantially larger, possibly infinite. If the universe is infinite, it contains an infinite number of galaxies, an infinite number of stars, and an infinite number of planets. In an infinite cosmos, where physical laws and constants are uniform, every configuration of matter that is physically possible must occur somewhere. This includes configurations identical to our own solar system, our own planet, our own civilization. In a truly infinite universe, there must be regions of space where the arrangement of atoms mirrors the exact conditions that produce you at this very moment. The implications of infinity are not just strange, they are genuinely disorienting in ways that no smaller number can produce. Whether the universe is infinite or merely unimaginably vast, the portion beyond our observable horizon is permanently inaccessible. This is not a limitation of technology. It is a limitation imposed by the laws of physics themselves. The universe is expanding, and that expansion is accelerating. In 1998, 2 independent teams studying distant-type EA supernovas discovered that the expansion of the universe is not slowing down under the braking influence of gravity, as most physicists expected. It is speeding up. Something is pushing space apart with increasing vigor. That something, labeled dark energy for lack of a better understanding, constitutes approximately 68% of the total energy content of the universe. Dark matter makes up about 27%. Ordinary matter, the atoms and molecules that build stars and planets and people, accounts for roughly 5%. The universe is overwhelmingly composed of substances we can detect only through their gravitational effects and whose fundamental nature remains one of the deepest unsolved problems in physics. Dark energy's accelerating push has a consequence that plays out across cosmic time with quiet but decisive finality. Galaxies beyond a certain distance are currently receding from us faster than the speed of light. This does not violate Einstein's relativity because the galaxies are not moving through space faster than light. Space itself is expanding, carrying them along. But the practical result is the same. Light emitted by those galaxies today will never reach us. They are beyond our causal horizon. We can neither observe them, communicate with them, nor be influenced by them in any way. And the number of galaxies crossing this threshold grows with every passing moment. The accelerating expansion is gradually shrinking the pool of cosmic neighbors with which we can ever have any physical interaction. In approximately 100 billion years, if dark energy continues behaving as current measurements indicate, every galaxy beyond the local group will have receded beyond the cosmic event horizon and redshifted into invisibility. A civilization arising in that far future epoch would look out into the sky and see only the merged remnant of the Milky Way and Andromeda, a single giant elliptical galaxy surrounded by a handful of gravitationally bound satellites. Within 1 trillion years beyond that, even the cosmic microwave background would have stretched to wavelengths too long for any conceivable instrument to detect. The evidence for the Big Bang, for cosmic expansion, for the existence of other galaxies would have vanished. Those future astronomers, no matter how brilliant, would have no observational basis for concluding that a larger universe existed. They would inhabit a cosmic dark age, isolated in a single galaxy, with the true nature of the cosmos permanently hidden from them by the expansion of space itself. We happen to exist during a brief window in cosmic history when the evidence is still visible. The cosmic microwave background still glows faintly in our instruments. Distant galaxies still send photons that arrive at our detectors after journeys of billions of years. The large-scale structure of the cosmos is still imprinted in galaxy surveys and gravitational lensing maps. We can still piece together the story. This window will not last on cosmic timescales. The universe is slowly erasing its own history, pulling the evidence beyond reach one galaxy at a time. One thing that the journey through cosmic scale clarifies is the relationship between time and space. In daily life, we experience them as separate things. Space is the gap between objects. Time is what passes while we move between them. But at cosmic distances, the two become deeply intertwined because light takes time to travel. This means that looking out in space is also looking back in time. The farther away an object is, the longer its light took to reach us, and the younger the universe was when that light departed. A star in our own galaxy that is a few thousand light years away appears as it was a few thousand years ago. The Andromeda galaxy, 2.5 million light years away, appears as it was 2.5 million years ago. The most distant galaxies the James Webb Space Telescope has observed are seen as they were over 13 billion years ago, when the universe was only a few 100 million years old. In the cosmic microwave background, the farthest thing we can observe shows the universe as it was 380,000 years after the Big Bang. Nearly 13.8 billion years ago. This means that looking at the sky is looking at a history book. Each layer of distance corresponds to an earlier epoch in the universe's evolution. Nearby galaxies show the present, or nearly so. Distant galaxies show an earlier time when they were younger, more actively forming stars, less chemically enriched, and structured differently. The most distant detectable signals show the universe before any galaxy existed, when the cosmos was a nearly uniform hot plasma. What the combination of all these observations allows is a reconstruction of the universe's full history from the Big Bang to the present, from a single vantage point in space and time. An observer on Earth today can see 13.8 billion years of cosmic history simultaneously, with each distance corresponding to a different epoch. This is not true of any other kind of science. Geologists must infer ancient conditions from rocks. Paleontologists must reconstruct ancient life from fossils. But cosmologists can observe ancient conditions directly, because the universe has been transmitting its own history in the form of light. And light does not forget where it came from or how long it traveled to get here. The cosmic microwave background is the oldest light. Its uniformity tells us that the early universe was almost perfectly smooth. Its tiny temperature variations, at the level of 1 part in 100,000, tell us about the quantum fluctuations that seeded all future structure. These fluctuations have been magnified by gravity over 13.8 billion years into the galaxies and filaments and voids we observe today. The pattern of those fluctuations encodes information about the total density of the universe, the relative proportions of dark matter and ordinary matter, the rate of expansion, the geometry of space, and the spectrum of primordial density perturbations. Each of these parameters has been measured with increasing precision through successive generations of instruments. The current standard model of cosmology, sometimes called lambda CDM for the cosmological constant, representing dark energy and cold dark matter, fits all of the available data with impressive accuracy. Its predictions match the observed properties of the cosmic microwave background, the distribution of galaxies in space, the abundance of light elements from Big Bang nucleosynthesis, and the acceleration of cosmic expansion revealed by supernova observations. This convergence of independent measurements on a single consistent picture is one of the strongest arguments that the broad outlines of our cosmological understanding are correct. The universe is old, large, expanding, flat, and composed primarily of dark matter and dark energy. These are not guesses. They are conclusions supported by multiple independent lines of observational evidence, each of which would be very difficult to reconcile with any significantly different cosmological model. What remains uncertain is the next layer of detail. Why does dark energy have the value it has if it represents the energy of empty space? Why is it not vastly larger, as naive quantum field theory calculations predict? This discrepancy between the predicted and observed values of the cosmological constant is sometimes called the worst prediction in physics, because the naive calculation overshoots the observed value by something like 120 orders of magnitude. No satisfactory explanation has been found. Why is there more matter than antimatter in the universe? The Big Bang should have produced equal quantities of each. Matter and antimatter annihilate on contact. If equal amounts existed, they would have annihilated entirely, leaving a universe of pure radiation and no matter at all. Clearly, the universe contains matter. Something must have produced a slight asymmetry in the very early universe, about 1 extra matter particle per billion matter-antimatter pairs, and that small excess survived the annihilation to become everything that exists. The process responsible for this asymmetry called baryogenesis, has not been identified. The known laws of physics do not produce enough asymmetry to explain the observed matter content of the universe. These are not small puzzles at the edge of an otherwise complete theory. They are central questions about why the universe has the character it has. A complete understanding of cosmology requires answering them. The program of attempting to answer them will take decades, perhaps centuries, of continued observation, theory, and experiment. It will require instruments we have not yet built, mathematical frameworks we have not yet developed, and conceptual vocabulary we have not yet invented. Each step will build on the previous one, as it is done from the first telescopic observations of Jupiter's moons to the mapping of the cosmic microwave background temperature fluctuations to within fractions of a millionth of a degree. Now stand back and consider the full journey. You started as a 1.8 meter figure on the surface of a planet, 12,756 kilometers wide. That planet orbits a star 150 million kilometers away. That star is one among 400 billion in a galaxy 200,000 light years wide. That galaxy is one of more than 80 in a local group, 10 million light years across. That group belongs to a supercluster 500 million light years in extent. That supercluster is threaded into a cosmic web of filaments and voids spanning billions of light years. And all of that exists within an observable sphere 93 billion light years in diameter, which is itself a small fraction of a universe that may be infinite. At every scale, the previous scale becomes invisible. The solar system vanishes into the galaxy. The galaxy vanishes into the local group. The local group vanishes into the supercluster. The supercluster vanishes into the cosmic web. And through all of it, you are here, a temporary arrangement of stellar material that evolved the capacity to look back at the stars it came from and measure, with real instruments and real mathematics, exactly how far away everything is. What makes this moment scientifically remarkable is not just the scale of what we can now see. It is that we are living during a period when new instruments are actively expanding what the species knows. The James Webb Space Telescope is returning images of galaxies that formed within a few 100 million years of the Big Bang, revealing structures that challenge existing models of how early star formation worked. The Euclid Space Telescope is assembling the most detailed three-dimensional map of cosmic structure ever constructed, tracing the distribution of dark matter across billions of light years. The Dark Energy Spectroscopic Instrument is measuring the expansion history of the universe with unprecedented precision, probing whether dark energy has remained constant over cosmic time or has varied in ways current models do not predict. The next generation of extremely large ground-based telescopes, with mirrors spanning 30 to 40 meters across, will observe the atmospheres of potentially habitable exoplanets and search for chemical signatures of biological processes. Gravitational wave detectors are opening an entirely new observational window on the universe, one that light cannot access. Merging black holes, colliding neutron stars, and possibly even processes in the very early universe generate gravitational waves that pass through matter unimpeded. What those waves will reveal about the cosmos over the coming decades is not yet known. The history of science provides little support for confident predictions about where the next surprises will come from. What it does support is the expectation that surprises will come, and that they will come from wherever the instruments are sensitive enough to see something no previous instrument could see. The universe, after all, is not running out of things to show us. There is structure at every scale, process at every epoch, complexity at every level of organization from the quantum to the cosmic. The scale of the universe is not a problem to be solved or a mystery to be mourned. It is the terrain. It is what exists, and existing within it, with instruments and mathematics and centuries of accumulated knowledge, it is possible to navigate more of that terrain with every generation that passes. One measurement, one observation, one carefully verified fact at a time. If you find this kind of exploration worthwhile, consider following along and subscribing. There is more territory ahead, and the instruments keep getting better. We are a rocky planet, in a suburban arm of an average galaxy, inside a local group, inside a supercluster, inside a cosmic web, inside an observable sphere that is itself an almost certainly tiny fraction of what exists. We have been looking at the sky with careful instruments for a few hundred years. We have learned more in the past 30 years than in all the centuries before. The investigation is ongoing. That is where things stand. There is another dimension to cosmic scale that tends to get overlooked when the conversation focuses purely on distance, and that is time. Not just the age of the universe as an abstract number, but what 13.8 billion years actually means when you try to place human existence inside it. If you compress the entire history of the universe into a single calendar year, each month would represent roughly 1,150,000,000 years. The Big Bang would occur at the very first instant of January 1st. The Milky Way would begin forming around mid-January. The Sun would not ignite until early September. Earth would form around mid-September. The first microbial life would appear on Earth in late September. For the next 3 months, essentially nothing visible would happen on the surface of our planet. Simple, single-celled organisms would drift through shallow seas. Multicellular life would not appear until mid-November. Fish with backbones would not evolve until late November. The first land plants would emerge in early December. Dinosaurs would appear around December 15th and disappear around December 26th in an extinction caused by an asteroid impact. The entire age of dinosaurs, 230 million years from their first appearance to their extinction, would fit into 11 days on this calendar. Modern humans, our species as it exists today, would appear at around 10:30 in the evening on December 31st. All of recorded human history, from the first writing systems of ancient Mesopotamia to the present moment, would occupy the final 17 seconds before midnight. The cathedrals of medieval Europe, the pyramids of ancient Egypt, the entirety of written science, from Aristotle to the James Webb Space Telescope, all of it falls within those last 17 seconds. Every civilization ever documented, every war, every invention, every discovery, 17 seconds inside a year that represents the age of the universe. This compression is not intended to diminish human achievement. It is intended to accurately represent the timescales involved. The universe was producing complex physical processes for billions of years before anything capable of observing it existed. Those processes operated exactly as they do now, entirely without observers. Stars formed, burned, exploded, and their remnant materials scattered into interstellar space. Galaxies merged and separated. The cosmic web slowly assembled its architecture of filaments and voids. All of this happened with extraordinary regularity and indifference, long before any chemistry on any planet anywhere had become sophisticated enough to ask questions about it. The question of whether this has happened elsewhere is one of the most consequential open questions in science. The conditions that led to life on Earth did not require any process unique to this planet. Liquid water is not rare in the universe. Carbon, the backbone of organic chemistry, is one of the most abundant elements produced by stellar nucleosynthesis. The chemical reactions that produced the first self-replicating molecules on Earth would have had the same chemical potential on any rocky planet in any habitable zone around any stable star. The number of opportunities for this to have occurred, given tens of billions of potentially habitable worlds in the Milky Way alone, and 2 trillion galaxies in the observable universe, is so enormous that the idea of Earth as the single location where life arose seems statistically improbable. Yet direct evidence of life elsewhere remains absent. The Fermi paradox, the apparent contradiction between the high probability of extraterrestrial life and the complete absence of any detected signal or contact, remains unresolved. This could mean many things. Life may be common, but technologically advanced civilizations extraordinarily rare. Intelligent life may arise, reach a certain level of technological capability, and then face pressures that prevent it from persisting long enough or becoming detectable across interstellar distances. The universe may be full of life that simply has not found us, or that communicates in ways we are not currently equipped to detect. Or the origin of life may be far more improbable than current chemistry suggests, requiring conditions so specific that even across 2 trillion galaxies, it occurred only rarely, or perhaps only here. The honest scientific answer is that we do not know. What we are doing about this uncertainty is actively improving. The next generation of space telescopes will be capable of analyzing the atmospheric composition of Earth-sized planets orbiting nearby stars. Certain chemical combinations, oxygen and methane coexisting in an atmosphere, for instance, are difficult to produce through purely geological processes and would represent a strong biosignature if detected. The detection of such a signature would not be proof of life, but it would be significant enough to demand further investigation. Simultaneously, radio astronomers are scanning larger and larger portions of the sky with greater sensitivity than any previous instrument. The Square Kilometre Array, currently under construction across sites in South Africa and Australia, will ultimately consist of thousands of individual antennas working in concert to form the most sensitive radio telescope ever built. It will scan for signals from other civilizations as a secondary mission while conducting its primary surveys of galaxy formation, dark matter distribution, and the nature of fast radio bursts. Fast radio bursts are themselves one of the more puzzling recent astronomical discoveries. These intense millisecond duration bursts of radio emission were first detected in 2007 and have since been found to originate from billions of light years away. Most fast radio bursts occur once and are never detected again. A small fraction repeat, some with surprising regularity. Their origin was debated for years, and the current leading explanation attributes most of them to highly magnetized neutron stars called magnetars, though the details of the emission mechanism remain under active investigation. In 2020, astronomers detected a fast radio burst originating from within the Milky Way itself, from a known magnetar about 30,000 light-years away. This provided the first direct observational link between magnetars and the fast radio burst phenomenon. The universe generates phenomena at every scale that current physics can partially but not fully explain. Dark matter is perhaps the most glaring example. It accounts for roughly 27% of the total energy content of the universe and roughly 85% of all matter. We know it exists because of what it does gravitationally, how it holds galaxies together, how it shapes the cosmic web, how it bends light passing nearby. But we do not know what it is. Decades of experiments designed to detect dark matter particles directly by waiting for a rare interaction between a dark matter particle and ordinary matter in a shielded underground detector have come up empty. If dark matter consists of weakly interacting massive particles, they are interacting even more weakly with ordinary matter than the most sensitive current experiments can detect. This has led to growing interest in alternative dark matter candidates. Axions are hypothetical, extremely light particles originally proposed to solve an unrelated problem in particle physics. They interact with ordinary matter so weakly that they would pass through the Earth without any effect under almost all circumstances, but they would have the right properties to account for the observed dark matter density. Several experiments specifically designed to search for axions are currently operating or under construction. Primordial black holes formed in the very early universe before any stars existed, have also been proposed as dark matter candidates. Gravitational wave detectors are providing new constraints on the abundance of such objects, though they have not yet been detected in the mass range that would make them the dominant component of dark matter. The nature of dark energy is arguably an even deeper mystery. The simplest interpretation identifies it as the energy of empty space itself, a baseline energy density that pervades the vacuum everywhere equally. This cosmological constant interpretation fits the observational data well, but the theoretical calculation of what this energy density should be, based on the known physics of quantum fields, produces a number roughly 120 orders of magnitude larger than the observed value. Something is canceling out almost all of the predicted vacuum energy, leaving only a tiny residual that drives cosmic acceleration. We have no satisfying explanation for why the cancellation is so nearly perfect, or for why the remaining residual has the particular value it has. This is not a new problem. It has been called a cosmological constant problem since the 1980s, and it remains one of the deepest unsolved puzzles at the intersection of quantum mechanics and general relativity. Resolving it will likely require a more fundamental theory than either of those frameworks separately provides. Whether string theory, loop quantum gravity, or some not yet formulated successor theory will provide that resolution is unknown. What is known with increasing precision is the observational picture. Space is flat. Expansion is accelerating. The universe is 13.8 billion years old. It contains roughly 2 trillion galaxies within the observable volume. Stars are ubiquitous. Planets are even more ubiquitous. 95% of everything that exists is made of substances whose nature we cannot fully characterize. The 5% that consists of ordinary matter, the atoms and molecules and particles of physics textbooks, makes up everything we have ever directly observed or touched. That 5% contains 400 billion stars in the Milky Way alone. It contains the Earth, the oceans, the atmosphere, every organism that has ever lived. It contains the instruments we have built to study the other 95% and the brains we use to interpret what those instruments report. The scale implied by all of these numbers does not become intuitive no matter how long you sit with it. The distances are genuinely beyond the range of spatial reasoning the human brain evolved to handle. What is possible, and what repeated engagement with the measurements does produce, is a gradually deepening appreciation for the structure. Not comprehension in the way you comprehend the distance to the nearest shop, but a kind of calibrated familiarity with the hierarchy. You know where the Oort cloud sits relative to the nearest star. You know where the Milky Way sits relative to Andromeda. You know where the local group sits relative to the Virgo cluster. You know where the observable universe sits relative to itself. And you know that it sits within something larger whose scale is unknown. This is not nothing. It is quite a lot, actually. The capacity to situate yourself accurately within this hierarchy, even without the intuition to feel it, represents something genuinely unusual in the universe's history. Whether it is unique or one of many instances remains the most consequential open question the measurements have so far left unresolved. The next few decades of observation will provide data that no previous generation of scientists could access. Some of that data will confirm existing models. Some of it will challenge them. Some of it, if history is any guide, will come from sources and directions that nobody currently anticipates. The history of astronomy is substantially a history of surprises. The cosmic microwave background was discovered accidentally by engineers troubleshooting radio equipment. Pulsars were first thought to be artificial signals. Fast radio bursts emerged from archival data that had been sitting unanalyzed. The acceleration of cosmic expansion was found by teams that expected to measure deceleration. The instruments currently operating and under construction are sensitive to phenomena at scales and energies that have never previously been accessible. What those instruments will find in the territory they are entering is genuinely unknown. That is precisely what makes the investigation worth continuing. The universe is large. The questions about it are deep. The tools for investigating it are improving, and the investigation is ongoing. That is where things stand. On this particular rocky planet, in this particular orbit, around this particular star, in this particular galaxy, within this particular observable bubble of a universe that is itself possibly an infinitely small fraction of what exists.